Okay, so here's our recap on lesson 4, which is the first lesson to use monogame. First thing we learned about was the game loop. Every game needs to have what's called a game loop to keep the game moving. There's typically some initialization before this loop takes place, and the contents of the loop is a bunch of stuff to do with updating the game world in general, like user input, AI, physics and scripting, and also a separate draw. Quite often these two things are not quite linked. Sometimes they run at different speeds because it has to catch up with lag. But ignoring that, they pretty much just both run in the loop. And that gives us what's called a frame rate. Every iteration, every trip around that game loop is called a frame. So when the screen refreshes, that's a frame. And so if it does it 60 times a second, you have a frame rate of 60 FPS. So you're probably well aware that affects the responsiveness of a game. You might have heard people talk about how the human eye can only perceive 24 frames per second. That's true for movies, but if you have 24 FPS in a game, it will feel a little bit unresponsive just because there is that slightly longer delay in milliseconds between pressing a button and the game doing anything about it. Okay, so generally speaking, you should aim for 60 to 100 FPS. If you can only get 30 FPS, most gamers will accept that, although they might grumble. We talked about sprites. A sprite is a name for a game object that has a position on the screen and a 2D image to draw there. A position can be represented in a 2D game by two coordinates, the x, which is horizontal, and the y, which is vertical, and those are in pixels on the screen, picture elements. That position can either be the first pixel in the image, and that's where it has been so far, the top left corner. But it can also be the origin point of the image, the point that it rotates or scales around. And if that's the case, the origin is usually, but not always, the centre of the image. To move a sprite, you would just change that x or y coordinate and then draw it in its new position. If sprites are moving, you usually want that to happen every frame, and you can also represent the movement as x and y values as well. The word vector itself comes from the Latin word meaning carrier, so the x and y of this vector carries an object from one place to another. So it's a velocity. If you apply this every frame, it's a velocity. You just add on velocity x to position x, add on velocity y to position y, every single frame, 60 or whatever times per second, and then you'll get smooth movement. So your direction and position can both be vectors, and a vector has an x or a y. This is actually what's called Euler's method, not Euler's. I used to call it Euler's, but apparently Leonhard Euler is Dutch or Belgian or something like that, so it's pronounced Euler. This is actually first order integration, which is kind of calculus. Technically it is calculus. You add the velocity on to position. You're integrating the velocity into the position of the object. You can then also have second order integration, which is where you integrate the acceleration onto the velocity, which moves its way down to the position, and that can get pretty complicated. The frame delta is the time between each frame being updated, and that's used in these calculations if you want accurate timing. If you're not too concerned about perfectly accurate timing, then you don't need to worry about that, but later on we will be using the frame delta, the 16 or whatever milliseconds between one frame and the next, to make sure that if there's any lag, then things don't fly about the screen. So Euler's method is an approximation of a curve. If you've got acceleration that affects the velocity, like acceleration such as gravity. So when you jump up into the air, you've got a negative acceleration pulling you back down again, and you'll jump in a curve. But if you use Euler's method, which is fairly simple, that will only approximate the curve, which doesn't really matter too much just now. If you're doing a heavy physics simulation, a tank battle firing with projectile trajectories and stuff, that might matter. But actually this matters more when things oscillate, springs and whatever. Maybe we'll see that later on. So we're using Euler's method. We're also using colours. If you did painting at school or anywhere else, you would have used subtractive colour. You start with a white page and you're actually subtracting colour from it. You're reducing the brightness of the colours by adding on pigments, which you might think you've probably been told the primary colours are red, blue and yellow, but it's actually slightly different. It's cyan, magenta and yellow if you want to be able to access the full range of colours using paint. But if you're using light, as we do on a monitor screen, then we're using additive colour. We start with a black screen and we increase its brightness. And in that case, the primary colours are red, green and blue, RGB for short. So these are the sort of representations of that. On the left, you've got additive, which we use. There's blue, red and green. Mix them together, you get cyan, magenta and yellow. Mix all three together, you get white. It's actually a pretty complicated topic, colours. For instance, did you know the colour, there is no such thing as the colour pink. The colour pink is a mixture of other wavelengths of colour, which is just perceived in your brain as pink. So it's very complicated, and some people can see colours that other people can't. But in general, red, green, blue will give you pretty much everything the ordinary person will be able to see. Subtractive, on the other hand, we're not going to use. In theory, if you mix cyan, magenta, you'll get blue, and so on. It's pretty much the same colour wheel rotated a little bit. Subtract all the colour and you're left with black. In theory. In practice, the inks don't really mix as well as that, and you'll get a sort of murky dark brown. But in a perfect world, you would get black. Refactoring we've used before, but we did it a lot this time. It simply means rewriting code to do the same thing in a better way. For example, better optimized so that it runs in less clock cycles or takes up less space in memory or on disk. It could improve reusability so that we could not duplicate code, reuse the code elsewhere. Or it could simply be done to make it more readable. You can split up your code so that the movement, the input, the AI is all in different places. Makes it easier to debug or extend the code to do other things. But just to reiterate, refactoring never changes the code, it still does the same thing. If you edit your code and it does something different, that's not refactoring. Then we looked at collision handling, and I think, in my opinion, next to AI, you're likely to find collision handling to be the hardest thing at first to learn. There's two parts to it. First is the collision detection. You have to find out when a collision has occurred. Or if you want to be really fancy, you can instead find out when a collision is about to occur. And then you do the collision response, which is what you do after detecting a collision. Does it bounce off? Does it get destroyed? Does it reset? What happens? Oh, I've changed the colour because this is all about Monogame now. So Monogame is a free open version of the XNA framework, which was developed by Microsoft. It handles a lot of generic boilerplate code that is common to very, very many games, such as the game loop, loading, and drawing. And this is, by the way, the icon for Monogame, MG. So the rest of this presentation is mostly about all the different things that Monogame provides that you as a developer can make yourself. Firstly, the game class, the most obvious one. It's a base class, so your game is based upon it, which gives you a whole bunch, you can inherit a whole bunch of stuff from it, like the game loop, the update, the draw, the initialize, and load content, etc. Typically, your class is based on game, and it's called Game 1 or Platform Game or something like that. The game has a bunch of methods. There's a constructor, which has got the same name as your name, and it creates the game, like setting up the graphics device, etc. It will have an initialize method to set up initial values for things. And it will have a load content to load in graphics, sounds, fonts, etc. These two are very closely related. The initialize actually calls up load content. And be careful about the ordering. So because initialize calls up load content, there are places you can put your own code that will happen before load content or after it when it comes back. And that does sometimes matter because you might want to, for example, spawn an object based on the size of the image that it has for it. And you need to load the image and come back before you can actually do that. So some people just put some of the initialization in load content as well for that reason. Nothing wrong with that really. You've got the update and the draw. Update changes the things that are happening in the game world. Draw represents the game world on the screen. And finally, after you exit, whatever you do to exit the game, it unloads content, which frees up memory used by graphics, etc. I didn't do any of that in the demo, and in most cases, at first you certainly won't have to do any either. I recommend you just ignore unload content until you've learned enough about coding that you're actually allocating things manually. That's the only time you would really want to deal with that. The game also has attributes. These are not methods, they don't do things, they store things. You've got a content attribute, which is a content manager. You can use that to load in graphics. That's pretty much all it does. If you've got a window object, you've got an attribute called window, which is a game window object. You can control the window, position, title, stuff like that. You've got an attribute for the target elapsed time. This is a time span which controls the frame rate of the game, or target frame rate. It's going to try to achieve that frame rate, but it might fail. There's a isMouse visible boolean attribute. This is whether the mouse is displayed or not. Simple. It's got a graphics attribute, one of the more complex ones, because that's your graphics device manager, which lets you access the viewport, clear the screen, create textures from scratch, that sort of thing. And the last one that's worth mentioning is the sprite batch attribute, which is a sprite batch object, but be careful with the capitalization so that you know which one's a class that you can't use to do anything except create other sprite batch objects, and the object which is actually used to collect sprites before flushing them out onto the screen. So back to those other classes that were mentioned. The content manager loads in assets such as textures, sounds, fonts, 3D models, etc. The only method worth mentioning is the load method, which looks a bit like this. You've got your generic type inside the angle brackets, and then a parameter, which is the name of the asset, not the file name, although it's almost certainly going to be the same without the .mp3 or .jpeg or whatever on the end. So when content load does that, it returns a texture or whatever which can be assigned to an object. Game window class. Every game has one called window, and it controls the window by doing things like setting the title that appears on the title bar, or accessing the client bounds, which is a rectangle containing the size of the window. It's not always the size of the viewport. You might have two viewports in a multiplayer game, for instance. There's a time span class, which we only used to to deal with the frame rate, and it's got a bunch of attributes. How many days, hours, minutes, seconds, milliseconds, or ticks is in that span of time. I would recommend mostly working with milliseconds. Ticks is so small it actually wouldn't really add up very well on a frame-by-frame basis. Whereas seconds is probably too large for a lot of things. Not everything, but a lot of things. The graphics device manager manages whatever the current graphics device is. There could potentially be more than one graphics device on a computer, so in a lot of cases there won't be. So the graphics device is the only one there, but bear in mind that's not always the case. So this allows access to whatever graphics device you're using, but it also can set whether the game is full screen or not. It's a boolean. I would recommend not making any games full screen until they're pretty much finished, because if the game crashes while in full screen, it's a bit more of a pain to debug it. The graphics device class then controls a video card. You can clear the screen, you can access the viewport and a few other things. That viewport has an X and Y coordinate for the top left corner of the viewport, and the width and the height, all in pixels. You can also get that as the bounds, which is a rectangle object. And you can access the aspect ratio, which is a floating point, a decimal value in other words, representing the ratio of width to height. So you've got widescreen or just standard definition screens there. The sprite batch class collects sprite textures into a batch and then draws them all at once onto the viewport. So begin starts collecting, draw adds a texture to the batch, draw string builds a texture using a font and then adds that to the batch. So it collects up all of the textures, and then when you hit end, those all appear on the screen for that frame. Textures are usually represented as texture 2D objects. So the class for representing images like sprites, each one has a width and a height telling you the size of the image. You can also use this method called fromStream. So you can load in an image without using content.load. You can do it just from a generic file name, which you might want to do if you're providing some kind of interface where the player can upload his own images or whatever. So this doesn't use Content Manager. Because it's static, you don't need to create a texture first. You can just say texture2d.fromStream, and it will return a texture 2D which you can store in an object. The color structure, it's not a class, it's a structure, which is not that different really, at the moment anyway. It defines a single color, which can be either partially or fully transparent if you wish. So there's the R, G and B values. A is alpha, which is the transparency. All of those are represented as numbers from 0 to 255. So if the colour is 255, 255, 255, it's white. If the colour is 000, it's black. Anything in between is the various colours you can have. So there's about 16 million possible colours there. Also with fully transparent to no transparency. But there's also a bunch of static, predefined colours like colour.blue, colour.red, colour.white, whatever, that you can use as well. The sprite font class stores data about a font, and you can use it to draw text. Every sprite font has spacing horizontally and line spacing vertically. The horizontal spacing is the space between each glyph. The glyphs are characters like letters and numbers and punctuation marks. And the line spacing is the space between lines. You can also use the measure string method, which will tell you the size and number of pixels if you were to draw a particular string. It doesn't draw it, it just tells you what size that would be if you were to draw it. And that's useful when positioning the text before you draw it. The vector2 structure I've mentioned already. It has an x and a y value within it, both of which are floating points. X for horizontal coordinate, y for vertical. They quite often represent pixels, but floating points gives us options to do other things with it, which is why you need to convert to integers when you make rectangles, etc. Vectors can be normalized. This turns it into a unit vector. It still has the same direction, but it shrinks or increases the length, so it's exactly 1 unit in size. That's handy for rotating things and stuff like that. We'll see that later on. You can also transform a vector. You can apply a matrix or quaternion transformation to do things like moving it around, scaling it, or rotating it. A lot of that you can do manually, but a matrix can sometimes make these a bit easier to use and reuse. That'll definitely be for a lot later on though. The rectangle structure, we've seen a few times now, it's got an x, a y, and a width and a height, all in pixels. But it also tells you where the top, bottom, left and right pixel of the rectangle is. It's got a method called intersects, which checks if two rectangles overlap, and it's got a method called contains, so you can see if a particular point or vector is inside that rectangle. Useful for clicking on things, etc. This one's not actually part of Monogame, the math class, it's part of .NET, but I've included it here because it's similar in some of the things it does. It's fully static, so you can use it any time to do any of these things, and it's just a bunch of math calculations, like absolute, which gives you the same number, but always make sure it's positive. And then trigonometry, things like sine, cos, tan, arctangent. Handy for turning angles and speeds into x and y, and vice versa. You've got a max and min, you give it two numbers and it tells you the biggest or the smallest out of the two. There's pow, which is short for power, and that's for squaring, cubing, power 10, whatever. And finally, the last one I'm going to mention is a constant called pi, which is going to be handy if you're working with angles, because a lot of things don't work in degrees, they work in multiples of pi called radians. We'll see that later. The keyboard class is static, it lets you access the keyboard whenever you like, and the main method there is called getState. All it does is return the status of the keyboard, which is an object of the type keyboard state. So the keyboard state has three methods worth mentioning: is key down, is key up, and get pressed keys. Is key down, sorry, tells you if a particular key is being held down right now. Is key up tells you if a particular key is released or not held down right now. Don't get those confused with the actual up key and down key. They are different. Get pressed keys, on the other hand, gives you an array of all the keys currently pressed. Don't rely too much on the keyboard. Keyboards are very old design and PCs, and certain key combinations will prevent you from actually pressing other keys. You can't guarantee that any more than 3 keys at once will be detected, just because of the hardware limitations on it. Okay, so the keys themselves are held in a keys enumerated type, or enum for short. An enumerated type just lets you specify a key on the keyboard rather than a numeric key code. Enumerated types associate names like keys.a, keys.z, keys.numpad0 Those names are all associated with an actual number which you don't need to know because the enum is taking care of it for you. There's a sound effect class that stores sound samples and plays them. The main method there is play, of course, but you can also create an instance. Because sound effects on their own don't have these kind of controls that an instance has, such as loop, pause, change the volume, etc. So sound effect instances are better if you want to be able to do those kind of things. But if you don't need them, then sound effect.play is a fire and forget method. You just type in .play and forget about it. There's also songs, but we'll get to them later. And that's it for now.